In this video, we will discuss about centripetal force. In my previous lecture, I discussed centripetal force, but now we will discuss very deeply in that matter. So, what is the definition of centripetal force? It says that when an object revolves in a circular path, the force that acts on the body in the direction of the center of the circle so that it keeps the object in circular motion is called the centripetal force. So let us take an example. When a stone A is when a stone A is wheeled in a horizontal circle, that means I rotate this stone it in a horizontal circle, uh, and this is my finger, and this is the point of the center of this circle, and I hold this center with my hand, and we connect this stone with a connect this stone with a thread, or we can say that a string. This is our string, and this is our stone. Then the tension T provides the centripetal force. That means when we rotate this string, we found a pain in our hand. When we rotate the string, we rotate the stone, we feel some pain in our finger, to our finger. Why it's happened? Because there is a tension. There is a tension towards the center. The centripetal force always points toward the center of the circle. So this tension is actually centripetal force F of C. So this tension is actually the centripetal force F of C. So these concepts is defined in our definitions. It says that when an object revolves in a circular path, in this case our stone is revolves in this circular path, the force that acts on the body in the direction of the center, the force that acts on the body of direction of the center, this body acts a force direction in the center of the circle of the circle, so that it keeps the object in a circular motion. This is the very important thing, the object in circular motion. So we know every time our stone wants to go through the tangent of this of that portion. Like if I say that when our stone comes at point A, it wants to break down its revolution with the tangent in the tangent path, but this centripetal force keeps its motion of direction. So if there is not centripetal force, then this stone will be uh, not moving in that path. Instead of, it will go in the tangent of this path. So this is the whole definition of centripetal force. So now we will see what is the what will be the formula for centripetal force. So we know, for force, force equals to mass into acceleration. Here our acceleration is central acceleration, and we know acceleration is, what is the meaning of the acceleration? uh, and the centripetal acceleration, we know the centripetal acceleration AC equals to v square by r. Here v is the velocity that in which that stone is moving, and r is the radius vector. In that case, this is the r of this is of this body, and the v is in which speed the stone is moving. So this is the, for centripetal acceleration we use this formula. We discuss it in our chapter 3. So here we will represent, we will instead of a of c, we will use v square by r. So this is one formula for finding out our centripetal force F of C. And we know there is a relation between linear acceleration and linear velocity and angular velocity, which is v equals to omega r. So we can write m equals to omega r whole square by r, from where we get m omega square r. So these are the two formula we will use to calculate our centripetal force. So we can write f of c equals to mv square by r, or you can say that m omega square r. So this is the formula we have to remember for solving the problem about centripetal force. Now coming to our next part, this is now in that section we will discuss about banking, angle of banking. So what is banking? When a when we see the motorcycle race or we cycle race, when the when the motorcycle racer or a cyclist moving through a band of a road, we see the cycler or cyclist or or the racer bend down towards the center. It bend down like this. The it bends like the picture I have added in my slide. Why it happened? Why they bend down? Because there is a theory of angle of bank. So now we will discuss this angle of banking in that lecture. So in our so to our so in this picture we see a cyclist is bending from its vertical position, because he or she have to cross have to he or she have to cross the bend of a road. So when he bending some so from this perpendicular part he bends down. So suppose he bends down with the angle of theta. This is our angle of theta, at which he bends down, and this angle is known as banking angle. This angle is known as banking angle. And and if this is the reaction force when the cycler is moving, it creates a force. So the force it creates is actually at that position, and this is the reaction force. So when this force is applied, and as this is the angle of theta, the the component of this the component with this theta will be f of cos theta, and in that section in that part, as this is the cos theta, the component along this path will be f of sin theta. So this is the whole what should I say, this is the whole concept of our banking system. Now we will derive some formula from that. Here we can see that when he or she bends down, so it creates a circular path, and there is a centripetal force. There will be a centripetal force in that portion, because if he or she wants to rotate in a circular path, and to not fall down, he or she will have some reacted force which opposes the centripetal force. So here he will she have some reacted force, as this is f of sin theta, that will be r of sin theta. R is the reaction force of F. R is the reaction force of F. So we can say, we can write that, we can write R of sine theta equals to centripetal force F of C. So these two forces is equal and opposes each other. So this cyclist revolves in a circular path and not falling down. And we know the for by the definition of centripetal force, we know the formula of centripetal force is m v square by r. Here, what is v? V at which speed the cyclist is moving, and r the radius vector it creates with the bending and the center of this and the bending the radius of the bending it creates with the center of the road. So now we find out a formula which is equals to r of sine theta equals to mv square by r. And there is another thing. Our here we can see our weight is acting in the downwards direction. So here we will find out a force that will acting on the upwards direction, and this is the reacted force R. So we can write R of cos theta equals to W, or you can say that M of G. So this is our equation 1 and this is our equation 2. From these two equations we can derive, if we divided 1 divided by 2, we'll derive sin theta by cos theta equals to tan theta. Tan theta equals to mv square by r into 1 by mg. So if we cutting down this mass, we can write v square by rg. From that we can see that to calculate this banking angle we don't need the mass. So there is so mass is not actually necessary to know the to calculate the thing. There is one thing we can find out. There is one, a thing is v and another one is r. So if v is greater, our banking angle will be greater. If v is less, our banking angle will be less. If r is greater, our banking angle will be less, and when our r is lower, our banking angle will be higher. So from these two concepts we can say that if when we go through a bend road, we will have to lower our velocity and higher our radius from the center of this road. That our banking angle will be at very small, so we will be stable in that section. So this is the whole formula of banking, and this theta is our banking angle. So we derived some formula of our banking angle, where we can see that to find out banking angle, the actually formula is tan theta equals to v square by r of g. So this is the formula of our banking angle. Now we will see banking of roads. When a car or train travels in around a curved road, it needs a centripetal force. Otherwise, the car or train can skid because of inertia of motion. To balance this inertia, outer part of the road or rail is made higher than the inner part of the inner part. So a centripetal force is created. This arrangement is called banking of road. So here we can see this is the inner part of the road. This is the inner part of the road and this is the outer part of the road. And we see that inner part of the road is outer part of the road is higher than the inner part of the road. Why we arrange this we arrange this thing in that way? Because to minimize the centripetal force and moment of inertia. This is the whole concept. So We take as an example when a car travels around an unbanked curve, the static friction between the tires and the road provides some centripetal force, but the magnitude is not sufficient, and hence speeding car is kicked from the road. So to avoid this thing, we use this kind of arrangements. Here we can see the inner part of the road is lower than the outer part of the road. So suppose this is a car moving in that direction, and we arranged some equations from that according. So here we see it creates an angle of theta with the horizontal direction, as it have to be in that direction, and this is our r cos theta, this is our r sin theta, this is our reacted force. So now we can see that our r sin theta opposes the centripetal force F of c. Now we can write r sin theta equals to mv square by r, and our r cos theta opposes the weight. So we can see the light m of g, and we derived this thing from in our previous slide, where we find out that the equation of banking is tan theta equals to v square by r of g. So when we have to bend a curve, our velocity will be lower and the radius will be higher. So if I suppose if I move from that portion, our radius is too low from the center, so then our theta will be higher. If I move through that portion, our radius will be higher and our banking angle will be lower. So we have to maintain these two when we have to drive through a curve. Now we will find out some solution for this x and h. H is the height of from the outer part and the inner part and the outer part. The difference between the inner part and the outer part. X is the length of the road. So here x is the length of the road, and h is the difference of inner and outer part. Okay. So from that we can see if this is theta, then we can write this theta and this theta actually are equal. So if this is theta, we can write sin theta equals to h by x, and we can write cos tan theta equals to h by root over of x square minus h square, as this is x square minus h square. And we know these thetas are too small. Theta are too small. When thetas are too small, we can write sin theta and tan theta are almost equal. Sin theta and tan theta are almost equal. So as thetas are too small, we can write this sin theta and this tan theta we can consider this as equal. So we can write h by x equals to h by of root over x square minus h square, root over x square minus h square. We can write this thing. So now we put this formula of tan theta, like it is equals to tan theta. So we can use this h by x in our equation 1. So we will get if we use this formula in our equation 1, we will get h by x equals to v square by r of g, or we can write h equals to v square x r of g. So this is the formula to derive height of inner the height difference of inner part and outer part with this formula. Hope you understand all the concept of banking and centripetal force. Please do subscribe to our channel and like this video. Thank you.